We are taking chapter number 2, electrostatic potential and capacitance. Electric potential due to system of charges. When we have a system of charges, that is point charges, if they are distributed discretely, that is they are separated from one another, while in certain system they could have been distributed continuously with each other. So in some system of charges, the distribution of charges could be mixture of these two distribution. So we'll start with the discrete distribution of charges. If you see in this figure, the points Q1, this one, this Q2, Q3, and there can be various Q4, let us take it up to Qn. These are distributed discretely, means they are discretely means there is no organized manner. So the position vector of this vector we can take for Q1, we can take R1, for Q2 we can take R2, and likewise Qn is Rn. So we need to find the electric potential due to this whole system of charges which are distributed at a point P, say this point. Say it has a position vector R. And for this, we will try to find out the electric potential due to every point charge, and then we'll sum them, we will add them. So this final V will be what? V1 plus V2 until Vn. And we know what is this potential. For with if you take 1, this V1, this will be 1 by 4 pi epsilon. This is because of charge Q1, so it will be Q1. The position vector is R1, so it will be R1. And we are taking it R1P. We are discussing the P because we want to find out at P because of Q1. So this is R1P. So R1P is the distance of P from Q1. This is very important. That is this one, R1 minus R minus R. This is R, distance of P from O. This is R1, distance of Q1 from O. So this will be the distance vector of P and Q1. Likewise, all of these we can write. R2P will be R minus R2, and say R3P will be R minus R3. Likewise, this will be R minus Rn. So this is the V. So we can just add them. We need to sum them. So we can use a sigma sign for summation. This is going from 1 to n, and this is 1 by 4 pi epsilon. Let us say it as K. This is Q1, Q2, Qn. So it will be Qi. I varies from 1 to n. And this is R minus, this is 1, 2. So R minus Ri. This will be the final potential. If we have a continuous distribution of charges, suppose in certain region electric charge is distributed continuously, means you need to imagine this region as divided in a large number of volume elements, and the volume elements are extremely having a very small volume. So the volume of such or this type of element, they are having a position vector R, and the volume we can say that it is this value very small, so we are taking d tau, and the d tau, this is d and tau. So it is some at volume of any position R vector, R dash vector is d tau vector or d tau dash. And at this position the volume density will be what? Or the volume density of charge, say it is rho, and rho will be what? The charge. If rho is the volume density, the charge will be what? This charge will be simply this rho, means volume density, into the volume, right? This rho is essentially Q by V. So what will be Q? Rho into V. Rho is rho, and this V volume, small volume, we have taken as d tau. So when we multiply them, we get a charge. And this can be treated as a point charge. So the electric potential due to this very small volume element at this point, say any point P, this point P having a position vector R is given by this dV, very small, 1 by 4 pi epsilon. This is rho R dash into d tau dash. This is equal to Q. This is the charge by R minus R dash. Say this is some R dash, right? Now we need to integrate because this is a continuous charge. So we need to integrate this equation over the whole volume, because we have taken just a small volume. We need to take it for whole volume of this distribution. So we get the total potential of this at, say, some point P. This can be written like this: 1 by 4 pi epsilon integration of the whole volume, rho d tau means rho r dash d tau dash r minus r dash. So if the distribution of this charge is uniform, we can take this, because we are integrating, as a constant. So we can take it as a rho. See, this is a constant, so we take it simply as a rho. A spherical shell with uniform charge distribution. See, we have just seen the electric potential due to continuous distribution of charges. Now a spherical shell with uniform charge distribution. So if we have a spherical shell with uniform charge distribution, how to go about the potential? So we have already seen that the electric field at a point outside and at a point on the surface of any spherical shell with uniform charge distribution is equal to what? The electric field obtained by considering just that the entire charge of the shell is concentrated at the center. Say this is the center, so whole of the charge is concentrated here. Again, any point which is outside or at a point on the surface, we assume that whole charge is inside. Okay, so we have obtained the electric potential from electric field. We know that V is equal to minus integration from infinity to r E dot dr. And for electric potential also, this entire charge, this we can consider to be concentrated at this, or concentrated at the center of the shell. So the potential of a point which is outside, say here, and at a point on the surface, say here, of a shell having charge, say q, and the radius, say from this point to this point is r, is given by what? V equal to 1 by 4 pi epsilon naught q by r, and this r is different. This r is the radius of this shell. This r is the distance. So this r is the distance of this point from the center. It can be like this. It can be like this. So this is a distance from the center of the shell. And also, we know that the electric field inside the shell is zero, because the point of discussion is the spherical shell with uniform charge distribution. It's a spherical shell. So the electric field inside this is zero. So during the motion of unit positive charge inside the shell, there is no work done. There is no work is required to be done. So the potential at all points inside the shell, they will be having the value which is equal to the potential on the surface. So all these points will have potential which is equal to the potential on the surface. So we can just write this. We can change this r with capital R, because at surface, this is r, this is the radius. So we can write V equal to 1 by 4 pi epsilon naught q by r, right? Equipotential surface. So what is the equipotential surface? See, the word is equi means equal, potential, we know about potential, so equipotential surfaces. So what is an equipotential surface? An equipotential surface is that surface on which electric potentials at all points are equal. The electric potentials at all points are equal. So the electric potential due to a point charge is given by, we know that this is the relation, V equal to 1 by 4 pi epsilon naught q by r. This r is constant. V actually, where V, if this r becomes constant, this is say some distance or radius, you can say, V will become constant. This will be also constant. Now we can say that for a single point charge, say q here, the equipotential surface are the surfaces of spheres drawn by taking the charge at the center. If you see this figure, the potential on which, this is the center, and these are the, if you take a circle, all the points in the circle are equipotential. This is one equipotential surface. This is another equipotential surface. Let me draw another surface which is equipotential surface. So the potential on these or two or more of, you can find any of these different surfaces are different, but for all the points on the same surface, say here, say here, say here, all the points on the same surface, the potential will be equal. So the electric field produced by, say, a point charge is along the this radial direction which is drawn from it. If you take plus q, they are in radial directions going away from it. If you take minus q, they will be coming inside. So these radial lines, these are normal to these equipotential surface at every point. So at a given point, the direction of electric field is normal to an electro or so equipotential surface which is passing through that point. So we'll try to see that or prove that this is true not only for a point charge but for any charge configuration. Suppose we have a unit positive charge and we give a very small displacement, say dl, this on the equipotential surface, and we do it along the surface, say from a given point. If this in this process, the work required to be done against the electric field will be what? Work will be, if this is very small, we take work as also small, dW will be equal to minus E dot dl. Why this is minus? Because we are working against the electric field by the external force. So work done will be minus E into dl. This is the potential difference between these 2 points. But the potential difference on the equipotential surface is what? Any equipotential surface you take, the potential difference between these 2 points will be 0 because they are having equal potential. So this E dot dl will become 0. E dot dl is what? E dl cos theta. That means this E will be 0 either, or dl will be 0, or some cos theta, means theta has to be 90 degree, cos 90 is 0. This theta is angle between E and dl. So E electric field, we are saying it is not 0. dl, the displacement is also not 0, so it is clear that cos theta is 0. So when cos theta is 0, theta has to be pi by 2, because cos pi by 2, cos 90 is 0. That is why we are saying that this electric field is perpendicular to this displacement dl. This dl is along this surface, we have just disclosed that in the beginning. So the electric field E is normal to the equipotential surface at that point. So like the electric field lines, the electropotential surface is also a very useful concept in order to represent the electric field. For a uniform electric field, say it is prevailing in x direction, the field lines are parallel to x-axis and they are equally spaced. While the equipotential surfaces, these are normal to x-axis. That means you can say it is parallel to yz plane. You can see here, these are the equipotential surface for a uniform electric field, right? If this is y, this is your z, this is your x. So this is how the electrostatic potential or electric field you can observe. So this is the electropotential surface of a dipole. This is minus, this is plus, so they are equal charges separated at some distance. And this is just for information. These are equipotential surface of a system of 2 positive, or you can say these are positive or equal charges, only for information. So equipotential surfaces for electric dipoles are shown here. The equipotential surface for a system of 2 positive charges of equal magnitude are shown like this. This is a dipole and this is because they both are same charges. Relation between electric field and electric potential. So now this is very important. What is the relationship between an electric field and electric potential? We have already seen where we discuss the electric potential V is given by minus infinity to P E dot dr from the electric field. Now if we are aware that the electric potential at a certain region, we can get the electric field from it. How? We have already seen that from the line integral of electric field between 2 points, say P and Q, we get what? Potential difference between these 2 points. So we say VQ minus VP, that is the delta V, difference of the potential, is given by from P to Q minus E dot dr. Now these points P and Q, they are, say, suppose we are very close to each other. Then for very small distance, or say then for such a small displacement, say dl, integration may not be required, or only one term E dot dl will keep. So dv will be this very small displacement. We'll just take E dot dr, we'll not use this integration, we'll just say for very small displacement, this dv, that is the potential change or potential difference, will be equal to E dot dl. Dl is the displacement. This dl is in the direction of E. So E dot dl will be what? E dot dl, E dl cos theta, because they are in both in the same direction, so it will be cos 0. So we get E dot dl. So what we get here, dv will be E dl, because cos theta or cos 0 is 1. So what do we get as E? This will be dv by dl. E will be minus dv by dl. So now this equation has given us, or it gives the magnitude of electric field in the direction of very small displacement, say some small dl. So this dv by dl is the potential difference. This is potential difference, this is distance. So this is potential difference per unit distance, and this is nothing but potential gradient. What is this? It is potential gradient, and it is given by, this is V by meter. And as we have just seen in the previous discussions and expressions, this one, because of this one, because E is minus dv by dl, the unit of electric field is also V by m, which is equivalent to your Newton per Coulomb. So if we have taken this very small dl, or we have taken the displacement dl not in the direction of electric field, say some other direction, then this minus dv by dl will give us some component. The component of electric field in the direction of displacement. So if it is dl is in this side, so we have to take, say, this electric field is here, so we have to take a component here. So the electric field is in x direction only, and the displacement is some other direction, say this direction. So we have 3 dimensions now. E will be equal to exi. We are saying that it is in x direction, so exi. dl can be in either in x, y, or z. So dxi, dy is j, and du zk. This is the vector representation of dl. Now what will be dv? It will be E into dl, E dot dl. So we just take the dot product of this and this. So we get only ex. Others, ij and ik will vanish. Only this and this will remain. So it will be ex dx. So ex will become minus, if you take dx here, ex will become minus dv by dx. In the same way, if the electric field is only in y direction, you get ey equal to minus dv by dy. If it is only in z direction, ez becomes minus dv by dz. Now if the electric field also has 3 components, say x, y, z, then from these equations, this ex will become del v by del x, ey will become del v by del y, ez will become del v by del z, and final E will be this I, this j, and this k. So this will be the final electric field if electric field has 3 components, x, y, and z. So this del v by del x, del v by del y, and del v by del z, these are nothing but the partial differentiation of this v. This is v, x comma y comma z, and with respect to what? X, y, and z. And more, if you see that the partial differentiation of this v, x, y, z with respect to x means what? It means the differentiation of v with respect to only x, del v by del x, and we have to take y and z in the formula of v as constant. We are not taking it as y or z properly, we are taking it as a constant. So the values of E at all points between P and Q, if you see the previous equations, the value of E at all points between P and Q, they will come into calculation. But if you see another equations, they give relationship between potential difference near a given point and the electric field at that point. So the direction of electric field is that in which the rate of decrease of electric potential where distance, which is nothing but minus dV by dr, is maximum, and this direction is always normal to the equipotential surface, right? And all this discussion is based on the property that electric field is a conservative field. Potential energy of a system of point charges. If you see here this figure, in a system of charges, 3 point charges Q1, Q2 and Q3, they are staying or lying stationary at these 3 points. Their position vectors from this origin are R1, R2 and R3. So we need to find the potential energy of this system. This OA is R1, OB is R2 and OC is R3. We can imagine that these charges are lying, say, at infinite distance from the origin and also from each other. But in this condition, the electric force between them will be zero because they are very far apart, and their potential energy will be zero. And the electric field at A, B, C are also zero. And in this type of condition, the work required to be done by external forces, or especially against the electric fields, in order to arrange them in this configuration, is stored in the form of potential energy of the system. So first we bring the charge Q1 from any infinite distance, from infinite distance to this point A. Right? So in this process, since no electric field is present, the work done by the external force against the electric field, say W1, will be zero. Right? Now the charge set on this Q1 produces an electric field and electric potential around it. So this potential due to this charge Q1 at point B, which is separated at, say, this one R12 from it, will be what? Say it is VB. It will be 1 by 4 pi epsilon naught, and this distance we are talking about. So it will be Q1, charge we are taking it as Q1, and distance from Q2, that is, this is R12. R12 is nothing but R2, this is R2 minus R1. So this will be R2 minus R1, and this distance we are talking about. This is R12, this is R2, and this is R1. So this will be R12. R12 is R2 minus R1. So the work required to be done by the external force to bring this charge Q2, now let us take this, from infinite distance to this point B will be same, we'll use the same thing. Q2, right, will be, VB will be 1 by 4 pi epsilon naught. See, this work done, this is what? This is VB, this is potential. But we are talking about the work done. Now work done will be Q2 into VB, because now Q2 has to be brought here. Q1 was already brought because there was no electric field. But now when Q1 is here and it has electric field around it, so now when Q1 is coming, it will experience the electric field because of this. So now there will be work done for bringing this Q2 from infinite to this point. So it will be, work done will be Q2 into VB because of this charge Q2, VB, because of this VB, because of Q1, there is a charge Q2 being brought from infinity. This work done will be 1 by 4 pi epsilon naught Q1 Q2 by R12. So if we want to consider the system of these two charges only, then the work done will be simply W1 plus W2, and W2 will be 1 by 4 pi epsilon naught Q2 R12. This is the electric potential energy of this system. Now this Q1 and Q2 will produce electric field, and Q1 will produce electric field. Now Q2 is also we have bought, so Q2 will also produce electric potential and field around this. Now the electric potential, because of this Q1 and Q2, and now we are bringing from infinity this Q3 also here. Because of this Q3 coming, and it is experiencing the electric field and electric potential because of Q1 and Q2, which is already there, which are being brought from infinity. This Q3 will experience now the electric field. So what will be the electric potential? We have to add the electric potential because of 1 and because of 2. So 1 by 4 pi epsilon naught Q1 by R13, this distance, and 1 by 4 pi epsilon naught Q2 R23, that is this distance, we add this. Then what will be the work done? Because we are bringing this Q3 charge, Q3 into this Vc, so Q3 into Vc will be W3. So when we add these three, the total work done, or the total work done to set these three charges in this kind of arrangement will be what? W1 plus W2 plus W3. So we add all these three and we get 1 by 4 pi epsilon we can take outside, and this is the final expression. So from this scenario, the potential energy of a system of n charges can easily be written as, this is Q1 Q2, Q1 Q3, Q2 Q3. So if we have, say, 4 charges, so it will be Q1 Q2, Q2 Q3, all the permutation possible, Q4 Q1, like this, by the distance between them. So this U will be 1 to n, and I should be less than j. See, always 1 is less than 2, 1 is less than 3, 2 is less than 3. So I has to be less than j. This is k, k is 1 by 4 pi epsilon naught, qi qj by qij. This is r, sorry, this is rij. Calculate the potential energy of system of charges which is shown in this figure. So the potential energy, but first let us analyze this figure. The total potential energy of the system of charges is equal to the sum of potential energy of all the pair of charges. So we have to find out how many pairs are there. This is a proper Q. So there are 12 pairs of charges. 12 pairs of charges. And the distance between the charges, electric charges in such pair is A, right? And 12 pair of charges of AB type. That means this type. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this G and C and F and B and B and C, all these kind of pairs, the distance between them is A, and there are 12 pairs. So the potential energy of these pairs will be, as we just saw in the previous discussion, K into Q, that is KQ square by A, distance between them, and because there are 12 pairs, it will be 12. Now there are how many pairs of AC types, like this thing, A and C. So this is diagonal. So A and C, this is E and G, this is H and F, like this. So there are again 12 pairs. If you draw it properly, you will be able to understand. I drew some for you, but now you can understand there are 12 pairs. So we just have to find one of these. So what is the distance between A and C? This is A, this is A. This is a cube, this is 90 degrees. So this will be A square plus A square under root. The distance will be A square plus A square under root, that is A root 2. Again, we'll use the same formula. This will be K into Q, KQ square. And A root 2 is the distance between them into 12. 12 means there are 12 of these. Now there is one more pair of type AG. Now this A and G, this kind of distance, AG, HB, like this. So there are only 4 AG type pairs. Now we have to find out this distance. What will be the distance? This will be equal to, or say, let us find out this distance. This will be this square plus this square. We just found out this AC. See, we just found out this AC. What was this? AC was A root 2. So we'll directly use this AC. This is A root 2. This is A. So it will be A root 2 square plus A square will be equal to this diagonal. So 2A square plus A square, that is AC was A root 2. So 2A, A root 2 whole square is 2A square plus A square under root, that this will be A root 3. So what will be U3? Again, K into Q square by distance into 4. There are 4 pairs. Now there are 8 pairs of electric charges which are similar to AO. What is that? See, this is O, there is minus 2Q charge, right? And this is 1, this is 2, this is 3, this is 4. So there are around 8 pairs like this. Again, now we have to find this distance. That means we have to find this distance. What is this distance? Let us drop a perpendicular here. Okay. So now this we know, this we know, and we can find out this one. It will be, see, the distance is very important. How you got that distance. This, if you try to arrange it, AO is simply this Ag by 2. Ag we have already found out, a root 3. Just divide it by 2. This whole was a root 3. We have to find half of this. So we just have to find this distance, or this distance, or so this distance, this distance. So this will be a root 3 by 2. Again, U4 will be k into q into q, 2q. This is q, this is 2q. So k into 2q. What is the distance between them? A root 3 by 2, and there are 8 pairs of this. So we have got u1, u2, u3, u4. Just add them. This is the final version. Just add them and just rearrange them. This is the final U, total potential energy, because of this kind of arrangement. So this is one more part of this discussion. Thank you so much and take care of yourself.